I'll share my presentation and then start with it. I hope you all can see this.
Yes, ma'am.
Okay. So let's begin. Swayam, India's first passively stabilized pico satellite. This is a story, and I would like to tell you this as a story only. A story where students decided what they want to do. I mentored them. College management provided all the funds. Professor Anil Sahasrabudhe, who was then director of COEP, now he retired as AICTE chairman, he was instrumental who took very great interest in this entire endeavor. And finally, 8 batches of students worked on the project, and on 22nd June 2016, Swayam got on board PSLV C-34 vehicle and took off. It completed 1 year of its mission life successfully on 21st June 2017, and as per guidelines, we had to kill the satellite so that the frequency which was allocated to Swayam could be freed. So, with this, we will begin. In 2008, a group of 3 students, Abhishek Baviskar, Mohit Karve, and Nishchay Mhatre, came to me with a request. IIT Bombay was associated with fabrication of their first satellite, Pratham. And that was also a communication satellite. So they wanted some other ground station to communicate with. Hence, we were approached, being close to IIT Bombay. And because Abhishek Baviskar had some friends who were working on Pratham, that request was sent to him that can you serve as a ground station so that we can communicate with COEP ground station. Then we got into talking, and really in those days, every day we used to brainstorm what can be done, what cannot be done. When discussing all these things, we four decided that we can, of course, try and serve as a ground station to IIT Bombay, who were much ahead of us in fabrication of satellite. But why can't we also make our own satellite? With this, we took the proposal informally to Sahasrabudhe sir, who was our director. He said, you can come up with the proposal and present it before the academic council. So we were given a period of 8 days to come up with a proposal. We made the proposal of a communication satellite of 1U standard. It was presented before academic council, and then we were given 1 year's period and a meager budget of 3.5 lakh to prove the feasibility of the project. So the work began. Right now, what you see on your screen, this is Swayam. Size of this satellite was 10 centimeter by 10 centimeter by 11.35 centimeter. As many of you are teachers, or all of you are teachers, so I'll tell that this is nothing but a chalk box size. In this, we have to pack all subsystems like power subsystem, onboard computer, the structure subsystem, antenna, solar cells for power generation, and the payload, that is communication PCB. What was Swayam? Two-way communication satellite to demonstrate use of ham band frequency for communication, and more important was demonstrate passive stabilization. A little while later, I'll come to what is passive stabilization. What Swayam did after it was launched into space on 22nd June 2016 at an orbit of 515 kilometers altitude, 97 degrees inclination. Every day, it orbited 11 times around Earth, out of which 4 passes were over COEP ground station. Here, you can locate COEP ground station. This blue thing which you see is the orbit followed by Swayam while revolving around Earth. And the yellow thing here is the communication cone. Whenever the satellite was at a particular location, the communication cone will go on shifting. Whenever it came over COEP satellite, this type of beep we could hear. This is the analog beep, which is called as a beacon. And this beacon is, I think, the best sound we had heard for the first time when it got launched into space. What was the scientific objective? To demonstrate passive attitude control. The utility was to provide communication platform in ham band, and we were not going to stop at one single satellite, but trying to do a constellation of satellites which can communicate with each other to characterize ham band for low Earth orbit satellites. These were the objectives of making the fabrication of the satellite. And the timeline, we started the work around November 2008, project initiated by a group of 3 students along with me. In January or February, we got a clearance to work on it with a small budget and 1 year period. In Jan 2010, we were in a position to present concept design review at ISAC Bangalore. Very significant step in satellite fabrication. These terminologies are specifically used at ISRO. So if any one of you is in a process of communication with ISRO for fabrication of satellites, you should be versed with all this. Concept design review is for the first time when your team presents before ISAC team why you want to build a satellite, what will be the rough specifications, what will be the timeline, what is your readiness, what is your budget. We came to know here in this review that to become eligible to fabricate a satellite, first we should have a functional ground station. What is a functional ground station? This is from where we began the journey of our satellite. We were contacted by IIT Bombay, just now I told you. So we had to build this ground station. When we started assembling all the requirements of a satellite. We came to know that we should have at least 2 working ham licenses to initiate the process of building a ground station. IARU Japan gives those ham licenses. And for that, your students should clear the exam conducted by IARU. COEP has one of the oldest ENTC departments, Electronics and Telecommunication, and we had a ham club. But unfortunately, we came to know that not a single ham license is in active state. So, first group of inductees had a job to work for about 6 months, register for the exam, clear the exam, and get minimum 2 licenses. If one wants minimum of 2 licenses, it's better to start with a minimum of 6 to 8 students, because we do not know how many of them retain the interest, give the exam, pass the exam, and get the licenses within that time frame. We got 6 working licenses within a period of 8 months. So the work began on ground station. Ground station has 2 segments: the ground segment and the antennas required for communication. We began with ground station requirements first. Antennas building is a very interesting story again. We wanted an antenna which was to be brought from France, brought from Germany, or US. These 3 options were available. The cost was more than 10 lakhs. Our complete budget was 3.5 lakhs. And that's why it was out of question that we will purchase this antenna. So we got to working on how to fabricate antenna. And within 1.8 lakh, we got different components. Some were brought from Germany, some were brought from France. Their pamphlets came in their own languages. We had to figure out where do they go and connect. And finally, within a period of 12 to 13 months, we were ready with the ground station. Whenever you are ready with the ground station, you have to communicate with International Space Station and convey your readiness. They send you a coded message and you have to decode the message and send them the reply. We had received an image of Yuri Gagarin, which we could decipher, reconstruct, and send back. And in October 2012, our ground station clearance was received. In about 7-8 months' time, in March 2013, the very significant stage at ISRO side was preliminary design review. About 22 to 23 students, 3 to 4 from each subsystem, along with me and Dr. Sutaune, who is now Vice Chancellor of COEP Technology University. We had been to Bangalore for this preliminary design review. There's a team of about 12 to 13 ISAC scientists who are subsystem in charges. They grill you for about 1.5 to 2 days on different aspects of subsystems, fabrication, your preparedness, and all. And finally, on second day, we got clearance for preliminary design review. After this comes a stage where ISRO is ready to sign MOU with your institute, and the MOU states that you have to complete fabrication of the satellite in next 2 years. So if you qualify at various stages, fabricate the satellite, which is satisfactory, then they will fly the satellite for free. In 2014, qualification model was fabricated. This qualification model is the most crucial thing, in a sense that after this qualification model is tested and found okay, you are not supposed to change even a pin in the entire project. So all your system requirements gets frozen at this stage. September 14, critical design review. Critical design review. This qualification model is as good as the main satellite because hereafter no changes are allowed. We completed this critical design review in September 2014, after which we got clearance of fabrication of the flight model. See, we got ready with the components in the month of December. January, new semester starts for engineering. Students went to ISAC Bangalore because final assembly of the satellite needs to be done in front of ISAC people. The testings should be done there, and then the satellite, after approval, certification, goes directly into their satellite storage facility. This was beginning of the semester to mid-February, 1.5 months time. In engineering, you all are aware that we have 3.5 months semester, out of which 1.5 month students were not present on campus. But their role of the mentor or the manager becomes critical. There were students from different years, different branches, and different specializations. They had their continuous assessment exams going on, T1, mid-sem, for which students were not present. I said, I'll speak with each and every individual, and don't worry, your exams will be conducted after you return. After February, mid-February, the fabrication was complete. All the testings were done. After approval by ISAC team, the satellite was stored in satellite storage facility. See, from February 15 till June 20th, almost 1 year and few months, 3-4 months, it was lying in the storage facility waiting for the right launch opportunity, because the altitude as well as the angle of inclination should be suitable for the launch. Whenever the satellite is in storage state, every 3 months, the team had to go there, carry out 2 to 3 days testing, get certification from ISAC team, and store it back into the facility. We could do that. And finally, the launch took place on 22nd June 2016. Such type of pamphlets are prepared and distributed by ISRO for every launch. Here, you'll be able to see Swayam, College of Engineering Pune, mass little less than 1 kg to provide point-to-point messaging services to the ham radio community. Along with Swayam, Satyabhama Sat was also launched in the same launch by PSLV C-34. Here was description of Swayam. It was 1U satellite weighing less than 1 kg. 1 kg is a standard for nano satellite. And this was 990 grams. So it became first pico satellite, even smaller than the nano satellite. Post-launch sequence of event: ejection from PSLV and OC is turned on. We came to know maybe 3-4 years before the actual launch that the satellite antenna, which is wound around the body, should be deployed 40 minutes after the deployment of ejection of the satellite. So the onboard computer team had to give that time for antenna deployment. So there are many such small things which we come to know eventually when you are in the process of making the satellite. Antenna deployment took place exactly at 10:28. First beacon was received. The beacon which I showed you earlier is the recorded first beacon. It came exactly at 11 o'clock, and that time when the first beacon came, we were in a vehicle coming back from Sriharikota to Chennai airport. And literally, when the beacon was heard, uh, we had a big team at COEP ground station. And from there, it was telecasted to us in a vehicle. And students who were in the vehicle literally started dancing in that Innova. First successful telemetry command. This is the digital signal. A beacon is analog signal, and first digital signal was received on 9:28 p.m. of the same day. Test message reception we could demonstrate and get on 23rd of June. And on 30th June, Swayam stabilized completely. We were expecting about 12 to 13 days as stabilization period, but you can see that on 8th day, Swayam stabilized completely. This passive stabilization story is also a very significant story in the sense for ISRO's big satellites, active stabilization is used, where stabilization of the satellite is achieved through electromagnets and through active attitude control. Our entire budget was so small for this satellite that we could not afford the kind of budget which is required for active attitude control. So, what to do? How to move on? Second most important thing is in the dimensions of 10 centimeter by 10 centimeter by 11.35, there is no space available for active attitude control. So how to do that? This was first major challenge which we came across. Our 8th standard or 6th standard students also know that Earth is a magnet in itself, and a magnetic needle stabilizes north-south as it aligns itself towards Earth's magnetic field. We use this trick, and this simple trick stabilized the satellite within 8 days and with a very meager budget of less than few thousands. We aligned permanent magnets perpendicular to each other and damped those magnets using Helmholtz coil. We worked in a very systematic way. Every year, a new project manager, student coordinator used to be there. Under him will be 6 subsystem in charges. Generally, the project manager will be from final year. Subsystem managers will be a combination of third year and final year students. Every year, there used to be one admin head who will keep a strict budget control over all subsystems. And I'm very happy to say that all my system admins were girls, and all project managers from 8 till 19 were boys. And this has worked very well. I started the story with Abhishek Baviskar. He is Abhishek, he is Mohit Karve, and he is Nishchay Matre. These three were project managers for first 3 years. Abhishek in 8th and 9th, 2008 and 2009, Mohit in 2010, Nishchay in 2011. This medal which you see in Nishchay's hands is the first one which India has received from International Amateur Astronomical Society. He is Shravan Aras, Rahul Kulkarni. He is the best project manager which I had seen over the years. Shreyas Kulkarni, Nikhil Sambus, they are all doing PhD or working in US now. Dhaval, he is the one who dedicated maximum of his time for satellite fabrication. From first year till fourth year, he worked, and when satellite was launched, he was the project manager. Umair, Deep, Ajinkya, they have all completed their masters by now and working at various institutes. This is at Gyati Award function. He is Umair. She is the admin manager of that year, 2019. Dr. B.B. Ahuja, who was director of COEP at that time, Anil Sasarbuddhe sir, who was then AICTE chairman, and myself. What were the challenges? Building a fully functional ground station, that was our first challenge. Why? For frequency allocation. Though you have a functional ground station, frequency allocation happens just one day before the satellite is launched, because This frequency is given to you free of cost by IARU. And this frequency allocation for free is available only for 1 year. So only one day before the launch, this frequency allocation is done. They give you a tentative range and you have to experiment with that range. But the actual frequency allocation happens exactly on time. What were what was another challenge was low cost passive stabilization. And for that passive stabilization, I'll show you the circuit diagram and all a little while later. Maximum weight permissible was 1 kg, and whatever you want to confine inside the satellite has to be within this weight budget. Total volume is restricted to 1000 cubic centimeters, and the geometry is near cubic, not perfect cubic, 10 centimeter by 10 centimeter by 11.35, and the tolerance which is allowed is zero point 0.1 millimeter. You can imagine the tolerance is thickness of your hair or even lesser in some cases. The total power which was available to run the entire autonomous satellite was just 2 watt. 1 watt LED we use as night lamp. And here an entire satellite is running with all 6 subsystems at just 2 watt power. The challenges were very strong and there was no tolerance at all. From HR side, those were the technical challenges, and these are challenges on HR side. Coordinating with academic and industrial entities for use of different test facilities. For when we started working on a satellite, we did not have a formal structure or permission or many of the testing equipment facilities, and therefore we had to approach, but we were fortunate enough that in Pune we have access to DRDO, we have access to Pune University, we have access to ARAI, CME, plus COEP, TIFR, IUCA, NCRA. We have used facility from each and every of institute nearby. And my role in all this was to set up communication with the right people, request them, explain them what we were doing, explain them how it was only for academic purpose, research purpose, and get the facilities. We got almost all the facilities for free. Coordinating with other ground stations to communicate with Swayam. Like we were approached by IIT, we had to communicate with other ground stations, and because our prime focus was demonstrate this passive attitude control and entire globe-wise communication, we had selected 10 different ground stations across the globe. Later on, I'll show you all the locations where we could establish the communication with. Venture into the domain which is not associated with academic credit. This is absolutely essential. If students select what they want to do, if they are passionate enough to keep aside their vacations, their picnics, even their exam time stresses, then only this is possible. Because why students get into any project is for free food, for free certificates, or for testimonials. But this team, which we selected every year, was really passionate about fabrication of the satellite. In fact, we were working on it since 2009. Until the end of 2015, 6 long years, there was no communication which said that on a particular day, the satellite will be launched. So every year in gathering annual social programs, there were jokes cracked on this team that they are making the satellite, but we do not know whether it will see the light of the day or not. So all these things really matter in a very long term project, because to maintain the same passion year after years, it was a dream for Abhishek, Mohit, or Nishchay. But finally, when the satellite took off, none of them was there. But subsequent teams took someone else's dream ahead. That is creditable. To maintain continuity in long-term project, I'll say that students used to keep changing every 1 or 2 years, 3 years maximum. Working systems were changing. COEP management also changed. 2 or 3 small satellite directors at ISRO also changed. And in all this journey of 8, 9 years, I think I was the only person who was constant working on the project alongside students. How to keep students motivated from different departments and working at different academic levels. These were the challenges with which we started working. Facilities used outside COEP: identify the facility, develop communication, obtain permissions for use, complete the task in time allotted. This is very absolutely important. When others are giving you a time slot, they are making space for your systems, and your students and you should understand the gravity and finish the task on time. Various facilities available at ISAC, VSSC, and SHAR. ISAC, all testing and fabrication. VSSC, matchmate review. SHAR, the final testing and integration of the satellite with the launch vehicle is done at SHAR. Antenna testing was done at University of Pune. Vibration testing were done at ARAI. GMRT for tests related to antenna, TIFR for photo detection. So we have used these main facilities outside COEP. This is the admin structure: faculty in charge or project manager. Faculty in charge was me. Project manager used to keep changing every year. Admin head used to be girls. Now we are coming to the actual subsystems of satellite. Structure and thermal. They were related with the outside body of the satellite and all thermal stability inside the satellite as well as outside the satellite. Here, students were primarily from mechanical, metallurgy, and civil engineering. Power system, the main job is to generate power, store power, distribute power, and in low power mode, to whom to give priority. In high power mode, every subsystem will get whatever power requirement they have. Communication subsystem. Of course, here the students will be from ENTC branch. Develop communication protocol. Develop antenna on board. Develop antenna on ground station. Get the signal, process the signal, send the signal. These are all the functions associated with communication subsystem. ADCS is attitude, determination, and control system. This attitude, determination, and passive stabilization that we will come a little later. This keeps ensuring that all the time the antenna on board is in favorable position to communicate with the ground. So its role is absolutely essential. An onboard computer works as brain of the satellite. It starts functioning the moment satellite separates from the vehicle. First job is antenna deployment. Next, switch on various subsystems. Start distributing power till the last moment when the satellite is to be killed. The kill sequence is also designed by students. 1 year is the life of any student satellite mission. Before 8 days, OBC starts asking, this is the date on which you have to kill the satellite. Do you really wish? If you get an extension, then this kill sequence can be stopped or reprogrammed autonomously. For 7 days, satellite will keep asking the ground whether you really want to switch off the satellite at this particular point. When finally you said yes, then on a stipulated day, the satellite stops communicating with the ground. It does not stop working. It does not stop moving. It just stops communicating because it has to free the antenna. So today also, Swayam would be traveling around Earth at its own speed, but we don't have any means to communicate with the satellite. Exactly, I think we are at our first break. So I'll stop sharing. We can interact for about a minute or two till 7:50, and at 8 o'clock, we will start again. Hello?
Madam, I have one or two questions. So can I ask?
Yes, fine.
Okay.
Go on.
My name is Prakash Yare. I retired in 2018 from our college, GSTI.
Okay.
Okay. So few questions are, the GSTI Department of Electronics has a call sign called VU2GSO.
Huh.
Okay. But at present, there are no active members in the department because all those students have passed.
Passed out. Okay.
So you are now suggesting that some students should be trained
Give
for...
the exam of IARU.
Okay.
They give you all the study material. There's very minor charge for giving their exam also. Only thing is students will have to work on their own for about 4 or 5 months and
Okay.
then appear for the exam.
Okay.
This license which they hold will be active till they graduate.
Okay.
So before that team graduates, again you'll have to send 2-3 more students for the exam and keep the license intact.
But the faculty also can become member and keep it active?
Yes, they can. If they are willing to appear for the same exam, they can.
You know, there is a Professor Ritika Nair and Ashwin Srivastava. So they did some practice of this Morse code. And I think that is one of the mandatory things there.
Yeah, that is the mandatory thing.
So, and rest of the thing is theory, which the faculty members will clear.
Will clear.
Second thing is, what was the call sign that you were receiving from your satellite?
VU2COE.
Receiving some message. So, what message?
VU2COE.
Oh, so the call, you were receiving VU2COE as the call every time it passed from there.
Yes.
And the last question is, the kill signal was given from your ground station or some other coordinator?
No. kill sequence is already fed to the satellite before it is launched.
Okay.
So you have to write the code, get it approved from ISAC,
Mm-hmm.
and then it is installed.
Okay. Now, but you said no, you can extend it because
Yes, there is a facility.
Once
That's
you
why
ask me-
it keeps asking you for say 7 days. If from ground station you give a command that don't kill the satellite, extend, then it keeps extending the.
but this command is given by COEP ground station or some
Yes,
other.
COEP ground station.
So you have a transmitter side also for.
Yes, it is two-way communication.
I see. So you had a
Though
transmitter.
it is half duplex,
Uh-huh.
in first half you can receive the signal, and in other half you can give the signal.
Acha. So okay. So at the same frequency you do that.
Yeah.
Acha. Okay. Thank you very much. So
Yes.
maybe a few questions after later on, and it was very exciting. In fact, I think the faculty members who are listening, Ashwin and Ritika and all that, because the time frame is very important. You have to keep patience for such a long
Yes,
time
yes.
to get the fruits. I mean, exclusive fruits, of course. So congratulations to COP once again. Okay, thanks.
Yeah.
जैन साहब और किसी को पूछना है?
मैम एक क्वेश्चन है मेरा. हेलो.
You can go on.
हाँ मैम, मेरा ये क्वेश्चन है कि इतना छोटा सैटेलाइट है और वो रॉकेट के जरिए लॉन्च हो गया है.
हाँ.
600 किलोमीटर है वो, एंड it is in free space almost.
It is.
Right. Now, when it is moving, and when it comes at the top of the Earth station, the Earth station start receiving the signal.
Yes.
So where is there is a question of power. Satellite is sending the power. And I mean, satellite sending the signal, which is having a very small amount of the power. Power is traveling 600 kilometer and it is reaching to the Earth station antenna. So and vice versa. Earth station is sending the signal. So there is a possibility we can send the amplified signal through the Earth station. So no doubt this power can go to the satellite. But the power which is coming, signal which is coming from the satellite is going to be very, very weak. So while traveling 600 kilometer, possibility of reception is how much?
Possibility of reception is 100%, I'll say, because you have to send a signal with a particular frequency which is allocated to you.
Okay.
And there should be a minimum 2 dB extra signal power available with you.
So what was the size of the ground station antenna? It was a parabolic dish.
I think it was a Yagi-Uda antenna.
No, it was Yagi-Uda.
Okay, I see.
Well, I've seen the photo. Starting when the ma'am shows the satellite, there was a picture of an antenna also.
Potato mesh antenna.
So it was the UHF and VHF frequency, I think.
VHF.
VHF.
Actually, if you have half duplex communication, you can do with either UHF or VHF1. But if you want full duplex communication, you require both.
Okay. And when
now we are working on another satellite which requires full duplex communication. So we are having both antennas now.
Right. When the satellite is revolving in the orbit, at particular point of time when it is coming at the top of the Earth station, Earth station is receiving the signal. So what I'm trying to say is some long-term communication was not possible. I mean,
no, long-term communication was not possible for two reasons. The memory storage SD card which was on board Swayam,
Ji, ji,
had a very small memory storage capacity.
ji, right.
Plus, because it was half duplex communication, whatever communication window you received, only half of that is utilizable.
Okay.
So, this was only for demonstration purpose, so we could do that.
That's fine. Ji,
Otherwise, you'll have to change the specifications.
ji. And what was the cost, ma'am? Total cost of this?
End to end, starting
No,
from
I mean,
2008
satellite cost.
till
Satellite
2016, it was 35 lakh.
35. Okay.
But that included all students' visit, food, stay, everything, not only fabrication cost.
So it is really a great achievement. In that sense, whole scenario changed. The students got motivated.
Yes.
They got a very good placement.
Mhm.
They understood the technology. Lot of industry got boosted up because of this.
Yes.
Ma'am, this is 50 minutes. So if you want to take break, 10 minutes break you can have.
Yes, yes.
And after 10 minutes, again, we are already there on the screen.
Mhm.
Then again, we can continue, ma'am.
Yes, yes.
Sure, ma'am.
I'm ready. I think we can begin.
Okay, okay.
Shall we start?
Yeah.
Is it visible?
Yes, madam.
Yes.
Yes, it's visible.
Let's begin with details on all subsystems one by one. Beginning with structure. Initially, we thought of making AI6061 solid cube, which will house all other components. But when we actually fabricated that cube skeleton, itself it weighed 650 grams. So there was no way we could continue with that kind of structure. Then we thought, let's make only the rails and jigs required for the structure, and the body of satellite can be made with the PCB themselves. So the weight can be contained less than 1 kilogram. Structure subsystem has to design structure, decide on the internal decking of different components, what should be placed where, such that they are sufficiently away from each other not to interfere with the working of each other. At the same time, everything should be confined in the available volume. There should not be overheating of any component which can damage the working or affect the working of other. All these things are prime concerns for structure subsystem. Antenna will be initially wound around the body of the satellite. When deployment of antenna is to be done, how it will get deployed? For that, we experimented with various mechanisms and finally settled on nylon nichrome mechanism. That means wind the body of the antenna around the satellite and tie it with nichrome wire using a nylon thread, such that in a single flash, in a single spark, the nylon will burn itself, pass heat to nichrome wire will burn out, and that will snap the antenna. Vibrations and thermal simulations are also in the purview of structure subsystem. Initially, when the satellite is thrown from the vehicle, PSLV has a multi-storied apartment complex-like structure. As we have different stories, different floors, at different floors, different satellites are placed. These small satellites, which go as piggyback, are stored at different locations to balance the weight of the satellite. And each satellite has to be confined in a box. For Swayam also, there was a launcher. And this launcher, fortunately, we did not have to develop the launcher because it was made by VSSC when IIT Kanpur satellite was to be launched. Whenever VSSC makes such launchers, one or two are kept spare, and one of that spare thing we could utilize. Before satellite is fitted into the launcher, we have to go and demonstrate at least 10 consecutive flawless ejections. Then only this size is approved. If satellite is smaller in size, then during the flight, there will be more vibrations inside the launcher that may damage the satellite. If it is very tight and doesn't come out in that stipulated time, it will not get launched at all. So this matchmate review, this is the technical term which VSSC uses. You have to demonstrate that 10 consecutive times the satellite gets launched in a single operation from the launcher. Launcher has a window. That window gets opened and satellite is thrown. So there are at the end rear, there are push plates. This push plate pushes the satellite out of the window and it is then thrown into space. A satellite has to experience 9G gravity. So all the components which are used inside should be able to take that 9G gravitational force. Thermal management, control, size, material, and tolerance should be exactly within the permissible limit. That is the prime job of structured subsystem. These are rails and jigs which make the exoskeleton of the structure. These four things which you see here, blue, these are lithium ion batteries. They are used for storage of the power generated. This is the red thing and the white cover is Teflon and Mylar coating, which restricts heat for flowing into and affecting other PCBs which are in the vicinity. I hope it works. This is exploded view of SWAYAM. Oh, just a minute. These are the solar panels which came out. These are the PCBs. These are the jigs and rails. These are support studs. These are the PCBs. One is power, one is communication, one is OBC on board. The red things and the white things are guide batteries, and these are the lithium ion batteries for storing the charge. Let's see this again. Guide rails coming out and jigs. PCBs. Antenna, magnets, and the battery. Next system is attitude control system. Function of attitude control system is to stabilize the satellite to attain the attitude favorable for communication. In layman's language, the antenna should always point towards Earth for favorable communication. If the antenna points away from Earth, then no communication will be possible. So, onboard detection of stability, achieving stability, and achieving favorable communication. These are attitude control system, for which generally bigger satellites use active attitude control system. So there are active electromagnets to continuously orient the satellite such that the antennas will be pointing always towards Earth's surface. This is active attitude control. Now coming to passive attitude control, which we used one permanent magnet along the antenna axis. This is the antenna. This red thing which you see is a magnet which is parallel to the antenna axis, and two pairs of hysteresis rods, HYMU. This is the material of hysteresis rods 1, 2, 3, and 4. 4 hysteresis rods which are in perpendicular to the red colored bar magnet to damp angular velocity. This is how passive attitude control is achieved. This is power subsystem. This system includes 4 lithium-ion batteries. Those batteries were provided by ISRO, 12 solar cells. Till engineering model, we used dummy lithium-ion batteries and dummy solar cells, which we locally purchased. But for final fabrication, for flight model, 4 lithium-ion batteries and 12 solar cells. There are 6 faces to a cube, 2 solar cells on each face are placed. Every time, at least 3 surfaces are pointing towards sun, and this sun side is producing solar energy, which is stored in lithium-ion batteries, and through circuits, it is provided to different PCBs to do their work. 2 watt total power generation and average battery voltage was 2.4 volts. Onboard computer. This onboard computer is the main controller. Antenna deployment, messaging, data acquisition, command handling, and in low power mode and high power mode. How to control power distribution to various systems. This is the function of onboard computer. Plus, final job is kill sequence. Operate the kill sequence and put the satellite to sleep. Communication subsystem, digital communication through a different board. Beacon for analog communication. Beacon was 15 words per minute. Data was transmitted at 1200 bps. This was received on first day. More than 1300 beacons were received at COEP ground station, and more than 2 MB of data was received through two-way communication, digital communication. These are the locations. A while earlier, I said that minimum 10 locations we had selected for communication. Here is COEP ground station. This is ISRO ground station. This is in Chandigarh. This is at Shar. And all these clustered in various continents. So we ensured that on each continent, we had at least 1 or 2 active ground stations with which we could demonstrate communication. This is how angular velocity is damped. This is essential to demonstrate the passive attitude control. This is T0, means when the satellite is thrown out of PSLV and it is launched into free space. These signals show that this is in tumbling state. Satellite is in tumbling state. Slowly, damping takes place, and after this point, we can say that it has stabilized and now it is working in almost a linear mode. This took place on 30th of June. Angular velocities along y-axis. Earlier was angular velocity stabilized along x-axis. So both xy stabilization we could achieve by 7th day. This is temperature profiling. Actually, this temperature should remain between plus 15 and minus 15, though the satellite is fabricated to work between limits of minus 20 to plus 45. But we could monitor that it is well within plus 20 to minus 20. So very good thermal stabilization was achieved by proper placement of Teflon, the mylar films, and keeping lithium batteries as far as possible from the PCBs so that heat will not reach them and will not damage the components. Very easy. There were 9 temperature sensors in that small space. Gyro temperature, onboard computer temperature, all PCB temperatures, and along the lithium-ion batteries, 3 sensors were put at different locations to monitor the temperature. And these are average temperatures plotted. The ground station component. Cross dipole Yagi-Yoda UHV antenna was built by students. Receiver to decode Morse coded analog beacon. It was provided with Doppler compensation, and communication has to be demonstrated in line of sight communication. For this line of sight communication, you have to select 2 highest locations which will not be disturbed by local wireless signals, mobile signals and all. Hence, COEP ground station is located on metallurgy top floor, and this line of sight communication is to be demonstrated at a minimum distance of 3.5 kilometers. So around Pune, there is in Pune, I should say, in Pune, there is a hillock called Parvati. At Parvati, a receiver was kept, and at COEP metallurgy terrace, transmitter was placed. With this, we could demonstrate line of sight communication. Later on, outside Pune city, there is a fort at height, which is Sinhagad Fort. So from COEP ground station to Sinhagad Fort also line of sight was demonstrated. All these demonstrations should be recorded and submitted to ISAC for approval of ground station. A rotor to control the orientation of antenna based on elevation and azimuth of the satellite. integrating antenna rotor and transceiver with digital interface of PC. This was all done by students in-house, no money spent on buying anything. This is COEP ground station. These are network analyzers. This is Yagi-Uda antenna array. This is egg beater antenna. And this is another 435 megahertz Yagi-Uda antenna. This is 437.025. This is the actual frequency which was allocated to COEP. Ground station, near the ground station, we have class 10,000 clean room, which was donated by COEP alumnus, who is now working on laminar flow workstations and all. So this was donated by his batchmates. Students were given a task to keep it clean, as no outside worker, no third party cleaner is allowed inside. But for years together, now more than 10 years, students have been maintaining the ground station well. This is the communication device which we had developed in-house, 10 such devices, and Russia, Germany, France, Argentina, all across the globe at different ground stations, they were given a dedicated ground station transceiver hardware was developed and provided to all these ground stations. Software for tracking SWAYAM was also developed in-house, and it was given to more than 10 other ground stations for checking. Students chose an innovative project, faculty supported the research, leaders provided all the required financial assistance. A while ago, someone was asking what was the total cost. Total cost from 2008 to 2017 was calculated to be 35 lakh plus something. But if we want to fabricate SWAYAM today as another satellite, then the cost would be less than 10 lakhs, because most of the cost goes in trial and error. Most of the cost goes into student visits, their food, stay, everything was provided by COEP. Of course, we kept a tight budget. Students will stay in youth hostel. If possible, if it is available, they used to live in ISAC hostel facility. They will commute by local bus. They will use trains for Pune to Bangalore travel. All this was kept strictly, and students also did not make any expenditure which was not to be approved by me, I will say. It took students about 6 years to fabricate, test, and transfer the 1U nanosatellite to ISRO. SWAYAM became India's first passively stabilized nanosatellite. It has successfully completed its mission life of 1 year, and ISRO was all praises for our students, because no other student satellite project gave them a complete report on post-launch review. Once the satellite is launched, everybody loses interest in it. It's done. They are happy, they are enjoying their party. But the development from day one till mission completion, that is 1 year after the launch, ISRO expects a written documentary evidence of all the stages in a post-launch review. It's again a very rigorous review before 12 to 13 ISRO subsystem in charges, and we submitted the documentary report in August 2017 to ISRO. This was the first and only post-launch report by any student team which is complete in itself. So I'll say that it is end-to-end success. In the beginning itself, we had quantified when we call that system has qualified, when we will say that it is a passing success, and when we will call that it is end-to-end success. And we completed each and every stage of SWAYAM and submitted the post-launch review document so as to make it 100% complete success. COEP does not have aerospace department or any even related course to the subject. No concession or any other academic benefit was given to students for working on satellite team. Even their final year BTech projects were different from SWAYAM. From 2008 to 2016, 176 students worked as a team from different years, different branches. They are coming from different demographies. This is very significant because all these students are not living in Pune. They are not having same financial strata, and they could keep all these differences away and work as a team. They have learned quite a lot through this project. Project progress, financial account, technical discussions with ISRO, VSSC, IIT, everything is well documented. It is in possession of the project manager and admin in charge. And from every year, when we have transition from one project manager to next project manager, all these documents are transferred. The email account remains same. It is transferred from each project manager to next project manager, so that in one single email, we have all communication intact. Whatever are failed experiments, I always used to emphasize that if you do not document a successful experiment, that is okay. But it is very essential that you will keep a proper documentation of all failed experiments so that we do not waste time and energy on failed experiment. We do not utilize the same ICs, same components which have failed. There were 2-3 things which failed during the experimentation. They were corrected and documented that never use these things. This is student driven, faculty assisted, and interdisciplinary research. See, every time we talk about interdisciplinary research, but here in each and every subsystem, you will see that the inputs which are required come from different technology domains. And no single person, no single team from one discipline will be able to make this satellite. So it is not essential to just give it a lip service, but work in a team which consists of different students, different backgrounds, and different specializations. Scientific objective was, oh, sorry, after completion of Swayam, immediately it was essential that student energies which are at highest are properly utilized for next and subsequent missions. That's why uh, in June end, we gave a 15 days break to all the students, because in those days we were giving demonstrations, which were giving presentations to different teams. After the launch on 22nd, we returned on 23rd from Shar. 3 students, myself and Professor Ahuja, we got a chance to go to Shar and witness the launch in person. When we came back, newspapers, TV channels, individual magazine bodies and all, everyone was flooding COEP campus, and we really had to control how many interviews we will give, who will go where to do the demonstrations and all. So it was a very chaotic situation almost for a month. We got a chance to meet Prime Minister. We got a chance to meet Chief Minister of Maharashtra. The very next day of launch, when we came back, the Minister of Higher and Technical Education came to COEP specially and felicitated the students. So it was a very chaotic situation, very busy days, but that was the right moment. I thought that we should start thinking about a new project, because when students are at their peak, they can think better, they can decide better, and we should come up with next project idea. So a competition was thrown, like each subsystem should come up with one payload, and then we will have a small conference where each subsystem will present their views, and from that we finalized another project for CSAT 2. CSAT 1 was Swayam, COEP satellite initiative. Satellite number 1 was Swayam. Now we are working on demonstrate orbit maneuvering using solar sails. What is the idea? Right now, chemical thrusters are used to move a satellite after it is launched at one altitude to take it to greater height. But this is polluting the environment. It is polluting LEO, and hence it is not advisable to use chemical thrusters. How, without dissipation of energy, satellite can sail from one height to other height, how it can glide. And the idea was like the way we play kite, with the wind bellowing, it goes up. Similarly, using Seebeck effect, we can glide a satellite from one level to other level. And what it will do? This is demonstration of sailing. But what it will do is to characterize the radiation density with altitude. Here, it is essential that the satellite slowly moves upwards and not goes into step-like jumps, so that the entire slice from 700 kilometers to 1000 kilometers away from the Earth's surface can be monitored for charge particle density. This is the new project on which we have started working. This is how the satellite will look. This is actually like a huge kite. These are solar sails. This is not CELL, this is SAIL sail, like a kite. Here are solar sails which will produce energy. And this, of course, is a two-dimensional picture, but the satellite will be three-dimensional. So between the sail and the solar sails, there will be avionics section of the satellite. This is team meet with Modi ji. This happened on 25th June. These are students who had gathered from, I'll say, all over India for the launch event. So this is the acting team plus 1 or 2 years senior team also. Here is team with Chief Minister of Maharashtra. This is our Board of Governors member, and these are students. In short, this is the gist, technical gist of SWAYAM. Scientific objective to demonstrate passive attitude control. Utility to provide point-to-point messaging in ham band. Launched at an altitude of 515.37 kilometers at an inclination of 97.5 degrees. Total weight 990 grams. Volume approximately 1000 cc. Not more than that. Launched on board ISRO's PSLV C-34 vehicle on 22nd June 2016. This is demonstration of passive attitude control because this is for the first time any student satellite team in India has demonstrated it. This red thing, you'll remember, it is the permanent magnet. These perpendicular four things, red, are hysteresis rods for damping the angular velocities. This yellow thing along the axis of magnet is the antenna, and this is the body of the satellite. This is how the passive attitude control was achieved. This is how damping of the tumbling took place, and we could demonstrate stabilization of satellite. This is done through attitude control system. This is the communication satellite communication subsystem highlights. Half duplex communication was used. Dipole antenna was used. Frequency 437.025 megahertz. Ground station initiates digital communication on UHF ham frequency. Autonomous Morse code coded beacon containing critical health monitoring data is transmitted every 90 seconds. And whenever the satellite comes over COEP ground station, all the data which is generated within that time frame is dislodged. This is power PCB in high power and low power mode used for communication. Onboard computer, chief source of intelligence on the satellite. Microcontroller based RTOS, real-time response system. This is fault tolerant and interrupt driven system. Main tasks: antenna deployment, load protection, implementation and testing of operating system, drivers, and file system, and final task was to kill the satellite. Power subsystem, power generation using 12 solar cells, protection of load from deleterious electrical faults, energy storage in 4 lithium-ion batteries. 1s4p is the configuration for battery arrangement. Power conditioning and distribution using DC-DC converter. Sensors to control critical electrical parameters. 9 such sensors were present on board. SWAYAM operated on 2 watt power only. Structure, form is 1U. The dimensions are fixed. 100 by 100 by 113.5. This is in millimeters with tolerance of 0.1 millimeter in each dimension. Mass 990 grams. This is what I was talking about. This is the launcher. Sorry for that. We use nylon nichrome mechanism for antenna deployment. This is thermal management and control. This is thermal profiling. Major achievements, SWAYAM was able to damp its velocities within 8 days. So passive stabilization happened in 8 days time. Completed its mission life of 6 months with all systems working. After that, 1 or 2 systems failed. First was SD card. So we are telling each and every student satellite team not to use SD card for memory storage on board. Communication system fully functional and messaging utility was tested successfully. SWAYAM operated in normal power mode throughout its life. It did never go to low power mode. So the power budgeting was done so nicely that never it went out of power. Within the satellite body, the temperature remained between plus 10 to minus 12. Actually, plus 20 to minus 20 was very much allowed, and even 45 to minus 20 was allowable, but it remained between 10 to 12. So thermal management worked perfectly well. Thorough demonstration was required to maintain continuity through 8 years of project duration. SWAYAM was an undergraduate project aimed at promotion of interdisciplinary knowledge. Scientific objective, orbit raise, this is for next mission. For solar sail project on which we are working right now, orbit raising and deorbiting, both are to be demonstrated. So first 6 months, the onward journey away from Earth's surface will take place. And for next month, because this will also be a 1 year mission life project. So 6 years for upward journey, 6 months for upward journey, 6 months for return journey. Utility, characterization of charged particle energy density between 10 MeV to 100 MeV. So proton detection will be primarily done. Various subsystems of nanosatellites are designed and tested in place. See, the basic advantage was we had functional ground station. We had half duplex communication. So building on the actually existing facilities was much more easier. So what we aim at, that first satellite took us 8 years for launching, but this project should be completed within 4 years to 5 years. It is a more complex project. It will be a 3U satellite instead of 1U. For 3U satellite, the total weight will be around 9 kg. And it will be like 1U satellite, 3 units on top of each other when it is launching. And after deployment, there will be a long sail coming out from the lowest section. From the top section, solar sails will come out, and in the central section, the entire avionics and other payload will be fitted. I'll stop sharing the screen. You can ask me anything. If I'm able to answer, I'll do that.
Ma'am, can you pass 10 minutes more?
Sure, why not?
Can you show some video or something? If you have.
I'll show you some interesting in-work things. Just give me a minute.
Yeah, sure.
I have 5 to 6 different presentations, and each has different details in it.
Some sort of video or something you have, if you have. 10-15 minutes of video files, if you have, about your laboratory or operational things.
Gents, our people can ask questions if they have questions.
Question time is 9 to 9:30, sir. Still 10 minutes is there.
See, I'll show you how the actual satellite works. Can you see the screen?
Yeah.
This is the satellite. When it comes over ground station A, it will ask the ground station, is there any message packet waiting for me? So this ground station, if it has any message, it will be given to satellite, it will store it. During its movement, when it comes over ground station B, ground station B has to ask the satellite, is there any message from anybody around for me? So the ground station has to initiate communication with the satellite. This satellite will then give the message that, yes, I have got a message packet from ground station A. It will deliver the packet. B will give the acknowledgement. It will be stored in the ground, in SWAYAM. When in second revolution, again the satellite comes over ground station A, it will say that I have got an acknowledgement from B, and the acknowledgement will be delivered to A. This is complete communication circuit. This is how environmental testing of the flight model was done. Vibration test with INLS as per VSSC specifications. Acceptance level is when the vibration is less than a certain value. Thermovac testing is done continuously for 180 hours. 3 short cycles, 3 long cold soak, and long hot soak. This entire cycle takes 180 hours. Before the launch, after the launch is announced, 4 days before the launch readiness. This is the final testing. Flight model fabricated is tested for all environmental tests. Ground station is ready. Frequency clearance is obtained. Plan for post-launch activities is also ready. Weekly basis plan and data logging and usage is also ready. all reports of design, interface, testing submitted to ISRO as per their requirements. And then physically, you have to carry that satellite actually like a small baby without any jerks in a special container which is completely free of tumbling and dams to Shar, integrated with PSLV, wait there till the launch, and then only after launch you are allowed to go away. This is here you can actually see that it's weighing 990 grams, and this is the weight budget where, sorry, the structure itself weighed only 272 grams. Solar panels 165. Batteries are the heaviest component always. 300 grams is the weight of battery. Communication, PCB, this and that. Total weight is 990 grams. This is INLS, which you can see now clearly. These are the guide rails. This is the spring with push plates. This is locked in the launch state. Then this window opens. There are rails inside. Push plate pushes the satellite and then it is thrown into space. These are vibrations allowed and what is the experimental data and all that. This is planned profiling. I said thermal profiling for 180 hours. This is the planned profiling and this is the actual profiling. This is the test facility for measuring the residual magnetic moment. Helmholtz cage was built by students in-house where satellite was placed. And I told you before that we had made a model. This was the aluminium AL 6061 complete frame that was used for testing. This is the half duplex communication, pass traced over COEP. And if anybody is interested in the block diagram of power system, this is what it is. From solar panels, there is boost converter, then it goes to buck converter. These are load protection, and this is then different subsystems are connected. So power is given to these in low noise amplifier, high power amplifier, and there are various temperature sensors, gyroscope, and current voltage sensors. These are all test signals. This is the energy budget. ISRO used to always tell us that our satellite is so over designed that there is hardly any chance that it will fail. This is the hardware architecture. For onboard computer PCB.
What is this kill, ma'am?
Hmm?
Kill.
Kill satellite means stop it from communicating with the ground.
Okay. Dad.
Huh. This is the 160-hour event timeline after the launch. Communication is turned off after 45 minutes. Antenna deployment happens then. Beacon data started. Latest satellite data parameters are checked every few hours. Messaging services and testing was done. Then other services testing. Finally, after 1 year, kill, abort, or extend lifetime. Here you will be able to see that if you want to continue with the same frequency, you can extend lifetime also from here itself.
Hello.
This is the communication PCB for flight model. This is the block diagram. I think it's 9. I can stop now.
Yes, ma'am. Ritika?
Yes, ma'am. Ma'am, I have some questions
Yes?
regarding the power supply.
Huh?
What are the specifications for solar panel? And then you are talking about boost converter. The buck converter is also used.
Yes.
So why these both converters are used? Any specific reason for this? And what are the specifications for a battery? As a
See,
power
batteries are gallium arsenide is used for
gallium
solar
arsenide.
cell, sorry, and lithium ion battery. Lipo battery and solar cells both come from ISRO only.
Okay, they
They do
supplied.
not rely on any other supplier, and they don't even give you specifications of the supplier.
Supply
Yeah,
also
they give you
they provided.
both these things free of cost. And it is
Okay,
given only at the stage when you come to fabrication of the flight model.
okay. So means solar panel, then it's
And batteries.
converters
And
and battery.
batteries.
All are supplied from the ISRO.
Yes.
Okay. So you don't have the specifications for all these things.
No. I have the specification. It is gallium arsenide cell,
Mm-hmm.
lithium ion LiPo batteries. But other than that,
Okay.
they will give you the batteries as and when you come to that stage.
Okay. So I think it depends on
Yes,
the
requirement of your a 3U
requirement of.
satellite. A 3U satellite will of course require more than 36 solar cells.
Okay.
This 1U required 12, and the power
Mm-hmm.
which was available was 2 watt. So,
Okay.
like that, if you have bigger panels, bigger requirements, accordingly it will change.
All right. All right. And the other
Ma'am?
thing, how COEP manages the budget for this satellite? Is it state government funding or the
No.
college?
See, for first satellite, it was completely spent by COEP.
Okay.
But for second satellite now, for solar cell project, I had 20.62 lakh grant from ISRO UOP, for which I had submitted the proposal. And from state government, we got 50 lakh funding. So we have
Okay.
70 lakh for the project 2 now.
Mm-hmm.
Plus,
Okay.
college has assured that if you run out of those 70 lakh, then college will provide whatever is required.
All right.
But it is very difficult to spend that money, 70 lakh also, because
I know.
primarily, solar sale, SAIL, is the most costliest component. And unless you sign an MOU and ISRO is ready to fly, they have approved the satellite project, till then, you can't buy those sales.
So
Okay.
that is last stage.
Yeah. Till then, what we did was using some golden glitzy paper, because how the sales will be folded and kept in that 1U unit. The total size is 40 square meters.
Okay.
How to store that sail
Just folding
when
it.
the satellite is going to be deployed is a major challenge. Different type of folding arrangements and all have been tried, but the sails should not tangle themselves. They should deploy properly. For that, the guide rails and the motors, brushless motors, will be using for that. So, for working on that, we have models, we have test signals built in classroom. How the guide
Okay.
rails will come out, how the sail will come out. Then 4 segments will be deployed. Then they will join each other to give you that